Hello viewers, in today's class we are going to discuss one important problem from integral inequalities. So in this session we'll see how to prove this inequality in which we have the integral 1 to 2 square root of 5 minus x dx is greater than or equal to the integral 1 to 2 square root of x plus 1 dx, right? So in this session we'll see how to prove this inequality by the method of graphs. So let us take this function as f of x and this function as g of x, right? So we'll take f of x as square root of 5 minus x and g of x as square root of x plus 1, right? And we'll graph both the functions on the same rectangular coordinate system. So to graph both the functions, let us take some particular values of x in f of x and g of x, right? So let us take here x and corresponding value of f of x. So let us assign some particular values to f of x. So let us take 0. So f of 0 is square root of 5. Then take 1. This is 5 minus 1 is 4. Square root of 4. So we have here 2, right? And then we can take one more value, that is 5. So 5 minus 5, when x is 5, 5 minus 5 is 0, so f of x is 0. And let us take one more value, say minus 4, right? So here we have 5 plus 4, that is 9. So square root of 9 is 3, right? So here we have the table for f of x. Now let us make a table for g of x, and here we have x and here we have g of x, right? So let us take x is equal to 0. So here we have 0 plus 1 1, square root of 1 is 1, right? Now let us take x equal to say 3. 3 plus 1 is 4, square root of 4 is 2, right? And let us take one more value of x. Take x equal to minus 1. So minus 1 plus 1 is 0. So g of x is equal to 0, right? So we have these values, and let us plot these points on this rectangular coordinate system. So let us first take f of x. So here we have x is equal to 0 and square root of 5. The approximate value of square root of 5 is 2.23, right? So when we take x is equal to 0, we have 2.23 somewhere here, right? Okay, then we have 1 comma 2, and here we have 1 and here we have 2, right? And then we have 5 comma 0. So we have we are now taking only 3 points. So we have these 3 points lying on f of x. So the graph of f of x, it goes like this. Here we can write it like this. So we have the graph, that is, it looks like this, right? So here we have the 3 points. This is 5 comma 0, and here we have the point that is 1 comma 2, and here we have the point that is 0 comma square root of 5. So this green curve, it shows f of x is equal to square root of 5 minus x. Now let us plot g of x. So now we have the first point 0 comma 1, right? So 0 comma 1, it lies here, and then we have minus 1 comma 0, and it lies somewhere here, minus 1 comma 0, and then we have 3 comma 2, right? So here we have 3 and here we have 2. So this point, it lies somewhere here, right? Okay, so now we can draw the graph of g of x. So the graph, it goes like this, right? So this is the graph of g of x, that is square root of x plus 1. So now we have the graph of both the functions. So now let us calculate the point of intersection, right? So this is the point of intersection of these two curves, that is the blue curve and the green curve, right? So the point of intersection may be obtained by equating f of x and g of x. So f of x is square root of 5 minus x and g of x is square root of x plus 1. So we have an equation here. So squaring both sides, we have 5 minus x is equal to x plus 1. So this is 2x is equal to 4. So x is equal to 2, right? So here we have x is equal to 2. So this is the point of intersection. When x is 2, the value of the y coordinate may be obtained by f of 2. So this is 5 minus 2, that is square root of 3, right? So the point of intersection of f of x and g of x is 2 comma square root of 3. So this is the point 2 comma square root of 3, right? So this is 2, this is 2 comma square root of 3. So now let us make some observations from this graph, right? Now see here, the limits of integration are from 1 to 2, right? So here we have 1 and here we have 2. So we have to integrate from 1 to 2, right? So this is the first observation, and the second observation is that the green curve, it lies above the blue curve, right? So this is the second observation. The graph of square root of f minus x is lying above the graph of g of x, that is square root of x plus 1, for all values of x, that is lying between 1 and 2, because here the limits of integration are from 1 to 2, right? So the graph of square root of f minus x always lies above the graph of square root of x plus 1 in the interval, because we are confined to the limits 1 to 2. So we are talking only about the limits, that is 1 and 2, right? So now from the graph, we see that this function f of x, it lies above this function g of x for all values of x belonging to this interval 1 comma 2, right? So we can say that f of x is greater than or equal to g of x in the interval 1 comma 2, right? So at x is equal to 2, both the functions coincide, right? And for other values of x, the graph of f of x always lie above the graph of g of x in the interval 1 to 2. So now here we apply an important property from definite integrals, right? See, if we have two functions f of x and g of x, as we have here, and the interval is given as 1 comma 2, and in general if we have the interval say a comma b, and f of x and g of x satisfies this property, then the integral from a to b of f of x should be greater than or equal to the integral a to b g of x dx, right? So this is an important property of definite integrals, that is, if f of x and g of x are two functions such that f of x is greater than or equal to g of x in some interval a comma b, then the integral of f of x from a to b should be greater than or equal to the integral of g of x from a to b, right? So here a is 1, b is 2. So now we can substitute the values here. So we have 1, 2, and f of x is the square root of 5 minus x dx. that is greater than or equal to 1 to 2 g of x is square root of x plus 1 dx, right? And that's it. This is the required inequality which is to be proved. So viewers, we can also prove this inequality geometrically by considering the graph of f of x and g of x. Right now, see, we know that the integral a to b f of x dx always represents the area bounded by f of x between these two limits. Right now, see, here we have the integral a to b g of x dx, which also represents the area, right? F of x is square root of 5 minus x, g of x is square root of x plus 1, a is 1 and b is 2, right? So let us consider the area bounded by f of x and g of x in this graph. So now see, here we have this point, right? So let us denote this point by A, this point by say B, this point by C, and this point by D, right? Now since the green curve, it lies above the blue curve, then we can extend this line up to A, right? So now the area bounded by this function f of x from x is equal to 1 to x is equal to 2 is given by a, b, c, d, a, right? So we have the area a, b, c, d, a, and the area bounded by this curve, that is g of x, that is the blue curve, from x is equal to 1 to x is equal to 2 is this area, right? So this area, so here we can take this point as the point say E, right? So the area is E B E B C D E, right? So E B C D E. So the area bounded by g of x dx is given by this shaded region, and the area bounded by this curve f of x from x is equal to 1 to 2 is this additional area including this one, right? So here we have this area also. So we can see from the figure that this area, that is area a b c d a, is greater than the area e b c d e, right? And this area represents this integral, which is the integral 1 to 2 square root of 5 minus x dx, and this is greater than or equal to the area represented by this integral, which is the integral 1 to 2, and we have square root of x plus 1 dx, right? So this is how by method of area bounded by curves we can prove these kind of inequalities. Hello viewers, in today's class we are going to discuss another important problem from integral inequalities. And in this class we are going to use a very important result from definite integrals which can be used to solve or to prove this inequality, right? So here we have to show that the mod of or the absolute value of the integral 0 to 1 square root of 1 plus x square times 1 plus x raised to 4 is less than or equal to 2 times square root of 10 divided by 5, right? So we'll see a new inequality or a new result which is also known as Cauchy-Squarge inequality, which will be used to prove this integral inequality, right? So let us first see the statement of Cauchy-Squarge inequality. So Cauchy-Squarge inequality states that if we have two functions, say f of x and g of x, right? And these two functions are integrable and continuous in the interval a comma b, right? We can also write it as x greater than or equal to b and less than or equal to a and b, right? Okay, so now if fx and gx are two continuous functions and integrable functions, and if the square of this function, that is f square x and g square x, are also integrable, right? So if the square of this function and the square of this function are also integrable in the interval a comma b, then the Cauchy-Schwarz inequality states that the absolute value of the integral a to b and f times g, that is here we are using the notation simply f for f of x and g for g of x, right? So the absolute value of this integral is less than or equal to the square root of the product of these two integrals, that is a to b f square dx, and then we have the integral a to b, and here we have g square dx, right? So this inequality is known as Cauchy-Schwarz inequality, and this inequality plays a vital role in proving a lot of other integral inequalities. So let us first take this integral as I, which is inside the mod function symbol, right? So we can take I is equal to 0 to 1 square root of 1 plus x square, and here we have 1 plus x raised to 4, and this is dx, right? Now let us express this integral like this, that is a to b f times g dx. So for this, what we will do, see, a is 0 and b is equal to 1, right? So lower limit is 0, upper limit is 1. So we can now write this integrand as 0 to 1. Here we have a square root of 1 plus x square, and then we can write it as 1 plus x raised to 4 dx, right? So now this function may be taken as the function f or f of x, right? And this function may be treated as g of x. So now we have an integral a to b f times g, that is the product of f and g. So f is square root of 1 plus x square and g is the square root of 1 plus x raised to 4. So now let us calculate this integral, right? So let us take this integral as I1. So I1 is integral a to b. Here a is 0, b is 1. So we have 0 to 1 and f square. So f square is square root of 1 plus x square whole square, and here we have dx. So this is 0 to 1, and simply we can write 1 plus x square because the square root get cancelled with this square, and we have simply 1 plus x square dx, right? Now we have a simple integral. The integral of 1 plus x square is simply x plus x cube over 3. Limits are from 0 to 1. Now substituting the limits and taking the difference, we have 1 plus 1 cube over 3 and minus, then we'll take 0. So this is 0 plus 0, and here we have 1 plus 1 over 3, that is 3 plus 1 over 3, that is 4 over 3, right? Now let us take this integral as I2. So I2 can be written as integral a to b. A is 0, b is 1, and g square. So here gx is square root of 1 plus x raised to 4. This is square, this is dx, and now we have 0 to 1, and square root sign it get cancelled with this square. So we have 1 plus x raised to 4. dx. So this is x. Integral of 1 plus x raised to 4 is x plus x raised to 5 over 5, and limits are from 0 to 1. Now we can substitute the limit. So we have 1 plus 1 raised to 5 over 5 minus 0 plus 0, right? So this is 1 plus 1 over 5, that is 5 plus 1 over 5, that is 6 over 5, right? So the value of I1 is 4 over 3 and I2 is 6 over 5. So now this Cauchy-Squarz inequality, it assumes the form, if we take this integral a to b f g dx as I, because I is our this integral, so we have mod of I less than or equal to, we have square root of I1. Here we have I1 and then we have I2, right? So this is square root of I1. I1 is 4 over 3, I2 is 6 over 5, right? So now we can simplify this expression. So we have here square root of, this is 3 to the 6, this is 2 for the 8, 8 over square root of 8 over 5. So now mod of I is less than or equal to square root of 8 over 5. This can be written as 2 root 2. Square root of 8 is 2 times square root of 2 divided by square root of 5, and we can rationalize it. So we have here square root of 5 over square root of 5. So this is 2 times, this is 2 5s are 10. So this is square root of 10 over 5, right? And this is our desired inequality, right? Because I is this integral. So mod of I is less than or equal to 2 times square root of 10 over 5, right? So viewers, this is how by making use of this important inequality, which is known as Cauchy-Squarz inequality, we can prove these kind of integral inequalities. Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integral inequalities. So here once again we have a very important problem from integral inequalities. So here we have to show that the absolute value of the integral 0 to 1 square root of x square plus x dx is less than or equal to square root of 3 over 2, right? So here without calculating the value of the integral, we have to show that the absolute value of this integral is less than or equal to square root of 3 over 2, or in other words we can say that the absolute value of this integral, it doesn't exceed over square root of 3 over 2, right? So let us start. So let us call this integral as I, right? So we have I is equal to 0 to 1, and the integrand is the square root of x square plus x dx. So we have to now show that the mod of this integral, that is mod of I, is less than or equal to square root of 3 over 2. So now to prove this inequality, here we'll make use of one important result from definite integrals, right? See, if we have two functions, say f of x and g of x, which are integrable and continuous in the closed interval a comma b, right? And if f of x and g of x are continuous function in the closed interval a comma b, and the square of this function f of x is also integrable, and similarly the square of this function g of x is also integrable in the interval a comma b, then we have a very nice result which is known as Cauchy-Squarz inequality, right? So the Cauchy-Squarz inequality states that the absolute value of the integral, that is a to b of f times g dx, right? The absolute value of the integral of the product of the function f and g from a to b is less than or equal to square root of the product of these two integrals. That is, the first one is from a to b, and here we have f square dx, and here we have a to b g square dx, right? So this inequality is known as Cauchy-Squarz inequality, and here the absolute value of this integral a to b f times g is less than or equal to the square root of the product of the integral, that is f square dx from a to b and g square dx from a to b. So we'll apply this result to prove this inequality. So now let us concentrate on this integrand. So here we have square root of x square plus x, which can be written as x times x plus 1, and here we have dx, right? So we can further write this integrand as square root of x times square root of x plus 1 dx. So why we have expressed square root of x square plus x like this? Because we can take this function as f of x, or simply f, and this function as g of x. So we can take f of x as square root of x and g of x as square root of x plus 1, right? So now we can apply this inequality to these two functions, that is f and g. So now we can write the absolute value of the integral, that is a to b. A is 0 and b is 1. So we have 0 to 1, f is square root of x, g is square root of x plus 1, and here we have dx. So this is less than or equal to the square root of the first integral, that is from 0 to 1, and here we have f square, right? So square of f is equal to x, right? So here we have simply x dx, and the second one is g square dx. So the square of the function g of x is x plus 1, right? So here we have 0 to 1, x plus 1, and this is dx. So now let us separately calculate these two integral. Let us call it as I1, this is I2. So I1 is integral 0 to 1 x dx. So this is x square over 2. The limits are from 0 to 1. So we have half minus 0, that is equal to half, right? And here I2 is also a simple integral. So we have I2 as 0 to 1 x plus 1 dx. So this is x square over 2 plus x. The integral of x plus 1 is x square over 2 plus x, and limits are from 0 to 1. So when we substitute the limits and we'll take the difference, we have half plus 1 minus 0 plus 0, that is 0, right? So this is 3 over 2, right? So now this inequality can be rewritten as mod of this integral. This integral is our I. So mod of I is less than or equal to square root of I1 and I2, right? So this is square root of I1 is half and I2 is 3 over 2. So now mod of I is less than or equal to square root of half multiply it with 3 by 2. So this is square root of 3 over 4. That is square root of 3 over 2. The square root of 4 is 2, right? So this is how we have obtained this inequality, that is the absolute value of the integral I is less than or equal to square root of 3 divided by 2, right? So viewers, this is how, by making use of this important integral inequality, we can solve these kind of integral inequalities.